Okay, so today we're going to be looking at how do we sketch graphs of polynomials when they're in factored form. So we've been talking about what is a polynomial, what are their different shapes, and how do we know their degree, leading coefficient, all of these characteristics of polynomials, all leading up to this. How do we take an equation in factored form and sketch the graph? So to begin here, I would like for us to look at this situation. So let's write an equation for a cubic function that has a leading coefficient of 2 and roots of -5, 0, and 2. So before I continue looking at this, I want to encourage you, at any point if you have questions, I encourage you to stop, pause the video, and write those questions down. And then in the Google Classroom page, write the questions in, and other students, other classmates, and myself can answer those questions as you go along. You're able to pause, rewind at any point. So let's see how this goes. So we look at this situation. So we know that we have a leading coefficient of 2, and we have roots of -5, 0, and 2. So we have this function, f of x. And if you recall, how we get these roots are from factors. So if I have a factor of root of -5, the factor would have been x plus 5. And then if I have a factor of 2, that would have showed up as x minus 2. And then a factor of 0, we have a factor of just x. So that would be great, that would be our function. But we do have a leading coefficient that we have to consider, so our leading coefficient is 2. So a cubic function that has a leading coefficient of 2 with roots of -5, 0, and 2. So we're going to revisit this in practice later on, but today's focus is how do we sketch this graph. How do we sketch that graph? And we're going to learn those skills today. So before we go much further into this, I want to go over some details we've seen in previous lessons. So I want to recap. If you have a polynomial, of n degree, what we saw in this week is that this polynomial has at most and at most is the key word here, at most n real roots and at most n minus 1 extrema. So that could be either local or absolute. So thinking about this, we saw, let's say we have a cubic function. Sorry, no, a quadratic. We'll start with quadratic. So a quadratic function. Well, we know that a quadratic function has a degree of 2. So what that means, what we're saying here, is a quadratic function has at most 2 roots and at most 1 extrema. And that should make sense. If we think of a graph of a quadratic function, so I say this, we see that we have 2 real roots and 1 extrema. So the reason why it says at most is we've seen parabolas where the entire parabola is above the y-axis. So in that case, if the entire parabola is above the y-axis, it does not intersect the x-axis at all, making no real roots. But we will always have one extrema for a quadratic. So this is just an example of what we're seeing here. So if we see a cubic function, so cubic again is degree 3. If you have a degree 3, that says again at most 3 real roots and at most 2 extrema. So based off our understanding of a cubic function, that again should make sense, because cubic functions we have seen can appear like this. So with this cubic function, we have 1, 2, 3 real roots, but we could have had less. And we have 1, 2 extrema. So just some concepts that we've seen recently, just reviewing those, getting pictures of those. So with that property, with that understanding, I also want to go over some vocabulary. Make sure that we are using the right terms in the right way, appropriately. So we have these 4 words that we've seen through this course and through Algebra 2. We have this term of a zero. We have what's called a solution, a factor, and an x-intercept. And as I'm sitting here writing this down, you might be wondering, well, aren't they all the same thing? Don't they all mean kind of the same thing? And I would agree that all of these do involve the same idea, but they look differently. So if I say that some number a is a root, is a zero of a function, what that means is, like x, let's just say x equals -3. That's our number. If I say that -3 is a zero, what that means is that this number is a solution of f of x equals 0. So if -3 is a zero, that will say that our function at that value equals 0. So far we have -3 is a zero, so therefore it is a solution because it makes our function equal 0. So with that, if a number is a factor, so again, let's say something is a factor of f of x. So if our 0 is -3, as we saw up above, that would make the factor x plus 3. So that may not be the only factor, but that is a factor. So with that factor, making -3 a 0, what we get here is that this number is going to be an x-intercept on the graph. So we have x plus 3 as the factor, which tells us that at -3 our function will equal 0, and gives us a 0 of -3, and on the graph will give us this point. So there's different words kind of revolving around the same idea. Just wanted to go over them before we move forward. So again, at any point, if you have questions, please pause the video and post your questions on the classroom page, and we'll go and address those when we meet. So moving on. So let's say we have, so again, just going over this again, if I have a factor, that factor gives me a 0, that 0 then gives me an x-intercept on the graph. So we're thinking of those 3 words in that progression. Factor leads us to 0, leads us to the x-intercept. So another term, this is going to be new for us. So another term that we are going to be looking at leading into our goal of sketching a graph is a concept called multiplicities. It took me a while to figure out how to say this word correctly. Multiplicities. To make sure I'm spelled it right. So to understand this word, let's look at the function f of x equals factor of x minus 2 cubed and x plus 1 squared. So we have this function. What a multiplicity is it looks at repeated zeros. Okay? And as I say that, you might think, well, we have seen this before, and you'd be true. We have seen this before on our first test. So we're going to look at this more right now. So let's say let's look at the factor of x minus 2. The factor of x minus 2, looking at our function, occurs 3 times. I know that by the degree it has. So the factor occurs 3 times. Therefore, what we say is the 0, 2, going to get 2 from that factor. The 0, 2 has a multiplicity of 3. So we're saying that the 0 of 2 is repeated 3 times. And we can build off of that and say, let's say we have the factor of x plus 1. So I'm going to pause here. If the 0, 2 has a multiplicity of 3, what do you think the multiplicity of this 0 will be? So in thinking here, you should be thinking that the factor occurs 2 times, which says that the 0, negative 1, has a multiplicity of 2. How'd you do? Did you get it? So, what does this mean? Again, this whole thing of multiplicity, why do we even look at this? Why is it worth, why is this worth discussing? What difference does it make if I have a 0 that's repeated? Well, it does something interesting to the graph. What we see, this is where we are generalizing this, so this is the key point now, is an even number of multiplicity means, here we go, the graph does not cross at the x-axis of that 0. So that still might not make sense. Well, we're going to see that. So we've seen this before, how something does not cross the x-axis. We've seen this before on our interval test. So if you think back to our first chapter, chapter P, we did this interval test. And many of you wanted to assume that at a number, we were always going to go from positive, negative, or negative to positive. Now I said, well, it's not always the case. So when we have an even multiplicity, what we see here is at a 0, the sign actually stays the same. So either it continues to be positive or it continues to be negative. There is no sign change with an even multiplicity. So visually on a graph, what we get is, so we go here, up. So this, at this point, at this 0, we would say that we had an even multiplicity, even number multiplicity. So now looking at, well, odd multiplicity, so an odd number. Now I'm thinking you probably can reason through, if an even number led us to not crossing the x-axis, an odd number means the graph crosses the x-axis. I'm going to abbreviate some stuff here. Does not cross the x-axis at the 0. In some cases, we'll see that it flattens out. We'll see examples of that later on. So where we see that with an even multiplicity, there was no sign change. With an odd multiplicity, that's where we're used to. We're used to seeing positive, negative, or negative, positive. So we see in our graph, our example, we see where we had an even multiplicity. We can also see 2 locations where we had an odd. So that's the whole purpose of multiplicity, to help us understand how the repeated zeros, we see up here the repeated zeros, how that affects our graph. So I think with this, we're ready to sketch a graph. So let's say we have the goal of this lesson. Let's sketch. So we have a factored polynomial. So let's use this example over here. F of x equals x minus 1 squared, and then x plus 3 cubed. So I encourage you here to go through this with me. As I'm going through this example, I encourage you to write this down as well, to follow along. So the very first thing we do to graph this function is to find the degree. Find the degree of this function. So if we look at our function, we have a degree of 3, 2, and 1. So the total degree of this function we would say is 1 plus 2 plus 3. We have a degree of 6. So again, we have the degree by looking at the total of our exponents. That's the very first thing. The second thing is we want to determine if our leading coefficient is positive or negative. So, how do we do that when it's in factored form? Because we can do that, we can find it quickly if this is all multiplied out. Well, in our factored form, our leading coefficient is still in our front. So we see we have a leading coefficient of, well, it's a positive number. So we have a leading coefficient that's greater than 0. And as I'm writing that down, I'm thinking, well, what if we have like a 2x minus 1 or a 5x plus 3? Well, if that's the case, then your leading coefficient will have to look at those numbers multiplied together. But since all of our coefficients are 1, our end coefficient will still be 1. So it's greater than 0. So we have that. So the purpose of doing that is we want to now use steps 1 and 2 to determine end behavior. Okay, so this we just talked about. How do we determine end behavior? Well, we saw that it's based on the degree of the function and the sign of the leading coefficient. So when we have an even degree and a leading coefficient that is greater than 0, what we know is our functions, the end of our function will look like this. They'll be both ends will be pointing up. What happens in the middle, we don't know yet. But what we know with an even degree, leading coefficient greater than 0, that the ends of our functions are both pointing up. We saw this in our previous lesson. So after that, now that we know what the ends look like, the ends of our graph, now we want to find the zeros by solving for 0. So we have our factored form: x minus 1 squared, x plus 3 cubed. And what we can say, and we don't need to multiply any of this out. We don't need to distribute an x or expand anything. We can say that for this to equal 0, we have x to equal 0, x minus 1 to equal 0, or x plus 3 to equal 0. So we have the first one done. Second, we would find that x would equal 1, and then x would equal negative 3. This will probably be the quickest step of this whole process, or one of the quickest steps, because we're just so used to doing this. We're so used to finding our zeros in this case. So with these zeros, what we added today was this idea of multiplicity. So that's where we look at the even or odd degree the factor has. So our x only had a degree of 1, so multiplicity of 1, which is odd, means that our graph passes through at that 0. Okay? Use a different color here. And then with our 0 of 1, we have to see it has a degree of 2, so multiplicity of 2. So I'm going to pause here, or you can hit pause. Since I have a multiplicity of 2, are we passing through or doing something else? If you look back in your notes, we should see, or you should know, that with an even multiplicity, this is where our function, we'll say, bounces off. It bounces off at that number. And then our 0 of negative 3 has an odd, it has a multiplicity of 3, so it's an odd multiplicity, which says that we are passing through at that point. Okay, so we're reviewing what we have so far. We have that from our degree and leading coefficient, we know that the ends of our function are both going up. And now we know that at the zeros of 0, 1, and negative 3, we know how the graph behaves around those zeros. So believe it or not, this is enough. This information is enough to sketch. So when we sketch, we're not trying to be perfect here, but we do have to have some guidelines. So we have zeros of negative 3 at 0 and of at 1. And we know that the ends of our function must be going up. So over here, I'm going up. And I know I have to cross through, I have to pass through negative 3. then at 0, at my next 0, at 0 we have to pass through that as well. So I come back up, I have to pass through it. And then at 1, with an even multiplicity, we bounce off of it. And so you look here, finishing this is a sketch. There are ways to get more precise with what we have. But you might be thinking, well, this is a degree of 6, as we saw up top. Why does it only have 3 zeros? Why does it only have 2 extrema? Well, it comes back to, it has 3 zeros because our zeros are repeating. We have a 0 that repeated twice, a 0 that repeated 3 times. So yes, in our very beginning we said at most a degree of 6. At most it could have 6 zeros. So here we see a degree of 6 only having 3. So with these 5 steps we get the information that we need to sketch a polynomial, if it is in factored form. So let's try another. So let's say we have the function. So this is going to be a problem where I encourage you, as I write this down, I want to encourage you to pause the video, right now and go through our 5 steps to get a sketch. Okay, so after pausing the video and after you trying this out, let's see how you did. So beginning, we want to find the degree. So looking at our factors, I have 2, 2, and then a degree of 1. So our total degree, the degree of our function, 2, 2, and 1, we would say this function has a degree of 5. So then think we have a leading coefficient. Is it positive or negative? Well, we look. 1, 1, 1. So our leading coefficient is going to be less than 0. The purpose of this was to say that we have an odd degree. So this was step 3 in the previous example. So we have an odd degree with a leading coefficient less than 0. So with that, we get our end behavior. So our end behavior in this situation, odd degree, leading coefficient less than 0, we see that our graph is going to look like this, with not knowing what's happening in the middle. So from here, knowing how the ends behave, now we find our zeros. So our zeros are going to be x plus 4 equals 0, x minus 6 equals 0, x plus 9 equals 0, which quickly says our zeros are negative 4, positive 6, and negative 9. Looking at our degrees, looking at the exponents of each factor, we have a multiplicity of 2. So we bounce at this 0. We have a multiplicity of 2 again, so again it bounces. But at negative 9 with a degree of 1, with an odd degree, here it passes through. So knowing how our ends behave, knowing where our zeros are, knowing what happens at each 0, this is enough. So let's place our zeros down. Nine, negative 4, and positive 6. So we see our end behavior. We have to have this and then this. So let's connect. So at -9 we pass through. At 4, -4, we bounce. We bounce off. And then at 6, all the way over here, at 6, we bounce again. Now, what happens between here, we don't know. So I can easily just give us a couple of extrema. And then at 6, we have a bounce. Oh, something I just noticed here. As I did this, I do have to be careful. It's a good thing to note. Our degree was 5, right? Which means that we can have at most 4 extrema. So we can't just be, lazy with what we do in the middle here. We have to still consider this. So we have 1, 2, and we're going to have this one over here, 3. So I can only have one other. So we're going to have to actually disregard this piece. I have to have that. So it might have been just simpler for me. I was trying to get all fancy. It might have been just simpler to go down, up, back down. So try not to get all fancy on you guys, but we do need to pay attention still to our degree with how many extrema that we can have. So we have it. We have the process needed to sketch a graph. So in the comments, you are going to post any questions, but before I leave and before I turn this off, I would like to give you one problem to do. One problem to do and to sketch. So sketch this graph. Okay? So when you come in, we're going to be practicing this skill some more, building off of this skill. But I hope this first try wasn't too bad, and I hope I'm talking clearly enough for you guys. I will see you tomorrow. And again, post any questions or comments that you have. Replay the video as many times as you need to. Hit pause and rewind as many times as you need to. And we'll see how this works out. Okay? See you tomorrow.